5 to 10 minutes. But from time to time, I might be able to cut the meeting short to make it on time. So hopefully, you don't have to wait for so long. So my expectation from you is to show up exactly at 1, but I'll do my best to show up at 1 as well. Now, how many of you are, well, most of you are second year, right? We have some third year and some fourth year. I remember seeing some of the faces before as well, right? Okay. All right. Okay. Let me go through my expectation. Before you start the class, you should have sufficient knowledge in statics. So let me point out what you need to know from statics. Now, usually in statics, we have the objects. And the objects that we have are considered particle or rigid body. And usually, if it is a rigid body, we will have summation of the force equal to 0, summation of the moment equal to 0 from the rigid body. If it's a particle, we have just summation of the force equal to 0. Now, what we will continue from statics is that we no longer going to have rigid body. So our objects will become what we call a deformable body. That means the objects can change the shapes, the dimensions may change, even if it's very slightly. You can grab more chair from the other room. Okay. So this is something that would be different. The rest will be the same. So it means that in statics, if we talk about those, it means we consider equilibrium. Or it means that we observe Newton's first and third law. And those laws actually help with the equations that we have. So summation of the force equal to 0, summation of the moment equal to 0. And in the deformable body, when we say deformable, it means that you have to have a knowledge from what we call engineering material. My question is, do you guys even take those classes? Engineering material, you never have taken any of those, so you never heard about phase transformation? Okay. That would be difficult for me. But we'll cover that in maybe this later part of the lecture, or maybe the next week. We'll have to cover that in a little bit more detail. When we have a deformable body, it means that if you have an object, and then you apply the loads to this. So for example, I apply the force to the objects. You would have the force applied, and they have this object attached to the wall. It means that this object by itself will have a deformation. And we'll talk about those deformation in more detail later on. So the dashed line that I tried to project onto this image is the exaggeration of what usually going on. So this is before, and then after you apply the loads, this is going to be after. So the initial length After you apply the loads, we have some sort of deformation. And that's going to be the knowledge from engineering material, which is something that I will also cover. And that's going to be part of the pre-knowledge that you should have for this class. But if you don't have those, that's fine, because I will definitely try to cover them before we kickstart the semester. So from here, we also need to know the basics of engineering principle from statics. In engineering principle, if you want to do any kind of problem solving, we need to do, number one, of course, you need to have some kind of problem statements. Maybe you need to grab a chair. I don't think we have enough chairs. Just look around first. How many people in this class? So, yeah, you can grab the chair from the other rooms. And my apologies, I didn't know that we could have the seating problems. So grab the chair first. So the problem statement is what do you want to find, the description. Usually this is going to be description and everything. In terms of that, you have to have a complete and thorough descriptions. And of course, with the description, you need to have like the objective of the problems. And then, this is going to be with objective. When I do the writing, those of you who already study with me, you probably know my short notes. W/ is with. If I say something like this, this is without. Okay. I'll write down, the explanation of those short notes that I have along the way. So in terms of the problem statements, you have to start working the problem by having what we call assumption. In assumption, we will have to assume different things. The scenario, of course, would be equilibrium, would be our first assumption. And that's going to be like the surrounding, the external factors that we have, like the force, the moment applied onto the objects. And we also need to have an object. And the object itself in this class would be the formable body. But then if it's a complete universe of deformable, you will have linear deformations. You will also have a non-linear deformation as well. And usually, in order to limit our skill and progress through the year, we will start with what we call a linear deformation, and that is also what we call elastic deformation as well. And we'll again cover those later on. In the assumption for this class, the object is not just deformable, but the object itself would have to be, usually we will have to consider is homogeneous. That means when you see the objects, you don't see any distinct inclusion. Of course, when you start working the material, like when you do the big picture, like this one, and if you see any defects on that, that's not homogeneous. Those defects could be carbon particle, it could be dust particle, it could be any kind of elements that you add into the objects itself, and it will definitely change the mechanical properties of the objects, and usually that's required more advanced or the rather advanced knowledge in order to complete the analysis. In this case, we only consider just the homogeneous. But in the homogeneous itself, we also need to understand that in order to do the analysis, it has to be isotropics. I saw those two at the faculty. I offered them the ride. They hitched the ride and they came like 20 minutes late. So if you guys around the faculty around like, a little bit before 1, you walk around in building number 2, you can hitch my ride. But my car can seat only about 3 people. So. Again, back to the object itself. When it's homogeneous, that means you see the objects as a solid objects, and the object itself doesn't have any kind of element that has been differentiated from the other part of the objects. We have to consider isotropic as well. That means you have mechanical properties that are the same in all directions. It means that, sometimes when you have an object, if the object itself, if you really look deep into the objects, usually all kind of metal, if you look at the microscopes, you will be able to see what we call the grain of the metal itself. And the grain of the metal itself may change according to the external force. If it has been pre-deformed, a lot of time you put it in the machines, do the stamping process, you do the extrusion process, you will have deformation. And with that deformations, the strength of the material along the line of the strengthening will be a little bit stronger. So we're going to say that the strength in this direction and in this direction or in this direction will be the same with the isotropic material or with the isotropic properties. And the reason for that is because if you don't have that assumption first, when you design any objects, you think it would not fail. But then again, sometimes the object itself has been covered, meaning that you put, for example, aluminum into the stamping machine, and you have a big stamping machine pushing it down. You have kind of what we call a plastic flow, and the object itself is actually pretty strong along the line that has been deformed. But then, on the other part that has not been stamped, the strength is actually less. And if you make an assumption that is all the same throughout the entire object, it's not going to be the correct way to make the assumption. But in this class, we're going to make things easy. We're going to say that everything is isotropics for this point. So that's going to be assumption. Now, in my class, it's rather easy because I don't want you to spend time stating all those assumptions. But in some of the more advanced classes, they will ask you, do you guys have to take fluid mechanics? No. You guys don't have to take fluid? What about thermodynamics?
No.
No. Okay. So again, in some of the class like fluid mechanics or thermodynamics, it is very critical to state the assumption because you have so many different kind of analysis depending on the assumption. For example, when you talk about compressible fluids, you have one theory that governs them, and you have like one way of doing the analysis. And in the non-compressible fluids, it's going to be something else. So, there are like 3 different classes, and that's why when you do that kind of analysis, you have to state the assumption. But in terms of the mechanics of material, we just say that, it's linear deformation. So it's a little bit easier for us. That's why I don't ask you to do that number 2. But number 3, this is very important, so I'm going to highlight it in red color. Defining the problem needs defining the variable as well. So in this class, we pay heavy attention to defining variables, and that is done through what we call free body diagram. We probably use the same abbreviation because you were studying statics with the 2 ajahn that used to be my student, so they pretty much know the terminologies and probably use the same. This is free body diagram. It is very important that you pay attention to doing this, because if you don't have anything written in the free body diagram and then you have like the analysis of it, I will not give you any credits because you are referring to nothing. So for example, if I have the picture like this, let's say I'm doing this FA, FB, and eventually I would ask you to do what we call a virtual section. This is going to be a virtual section. And usually the right way is to do this section and have the internal loads. Let's say for example I have this force and the internal load is like this, and I call this internal load FAB. Along the way you will see these terminologies quite a lot, but the thing is, if you don't have this picture, so for example, this is what you're supposed to have, and usually from here I will take this free body diagrams and say summation of the force in the x-axis equal to 0, and I will have my FA plus FAB equal to 0, and my FAB equal to FA. Now, a lot of times you see this over and over, and you kind of think that this is really easy. I can do everything in my head. I can just say that FAB equal to FA right away without showing the steps that I'm making right now. And when you do that, I will give credits unless you have listed everything that I have written here. So for example, if you don't have these parts and suddenly you kind of do everything in your head and you got this right away, even though you understand what's going on, I understand what's going on, but in terms of the engineering report or in terms of the things that you need to get money, usually you have to do the summary or the report for a superior or to someone else. If you don't have the detail right up, this would be nothing to you, because I would be asking like, what is this? And I would be referring to this picture, and I don't see that in the picture. So anything in your equation, always check and make sure that when you look back to the picture, it's there. Sometimes things are pretty obvious. You found that it's really easy. You got the right answer. And many people who got the right answer in the end didn't get half the credits that they deserve because they didn't go out and write all the detail that was needed for the class. So do not skip anything, okay? So again, do not skip steps. This is very important. Now, in terms of the free body diagram, this is something that it's worth mentioning. I'm going to talk more about free body diagram. In free body diagrams, you will be asked to draw, or sometimes you don't get the question asking to draw the free body diagram, but you should know that you're supposed to be doing that. So one of the things that I really care about is this. If you have the force, sometimes you do it in a rush, and the force itself do not touch the objects, I will make a circle. And I will say like minus 0.5, so that's always 5% off. You should have axis. So x and y axis. And the axis itself should be referring to the objects. So if you have the axis out like that, floating out there, I'm not going to take that. So the objects, if you want to have the reference point 0 over here, the axis should be like this. Or you can have it over here, I don't care. This is okay, but this is not. I don't want the axis to be floating out in the air. You have to make sure that the axis is within the objects. Or it can be a reference to the objects. Because we are dealing with the objects with dimension, so I expect that you have some sort of reference that you can go back to. Now usually with this, if I have x, I have y-axis, it means that my z-axis should be this way. It actually follows I cross j equal to k. It means that if you, for some reason, trying to do things differently, like you do x and y and say this is a z-axis, I'm not going to take that as well. It has to follow the right-hand rules. So this is wrong, this is right according to the right hand. So as long as you have x, y, and z-axis according to the right-hand rules, I'm okay with that. And also, it means that when you do the process, for example, I will, I will do this one more time. So let's say that I have this free body diagram, and I may have a y, a x, I may have an a like this, and maybe I have like 200 Newton, and let's say this is 400 millimeter. So for example, this one, if I say x and y like this, usually the protocol is to do, to find the reactions at the support. You will be saying summation of the force in the x equal to 0. You do the mapping process according to the axis that you draw. So it means that you will have ax going to the right. This is a positive ax. You don't supposed to be like doing something else, because I'll show you like what happened when you do something else. So this is something that follow the mapping process, using the picture map with the governing equations on the right. But sometimes people say summation of the force in the y equal to 0. You know right away that going to the right here is positive according to the x-axis. You know right away going up is positive, but usually I don't ask you to do that. What I ask you to do is, when you do the mapping process, you should have, how many students are in this class?
60 something.
You guys check the 60? 60? Okay. Seems like a lot. I will ask them if they can find us a bigger room next week. My apologies, I didn't know that it's going to be this big. So let's back to this. So we know that in terms of the mapping process, AY is going up, 200 is going down, so it's going to be a negative values. So this is going to be the way to do the write-up so that you can look at the picture, map with the axis, write it out, and in the end process, if you do anything wrong, you can always go back and make changes. You will not be able to make everything at 100%. Neither do I. You know, every week that we meet, when I do the write-up on the board, there's a chance that I will make mistakes. But the thing is, when I do make mistakes, at the end of my problems, I can browse through, go all the way back, and I can spot that error very quickly. So you can identify the mistake very easily too, because if you keep following my write-up, you will be able to see that right away. So like this, a lot of time people would be skipping the mapping process on the second line, and they do everything in that head and do the write-up from the first line to the third line. Now, people who didn't have the governing equations will not get any credits at all, because I've seen many of those when I do the grading. If you don't have the governing equations, you will get 0 for the write-up. If you don't have the mapping process, it means that it's going to take more time for me to check the error if you have one. If you don't have any error, sometimes I do let it go. Say, well, you're smart, you know, you do everything in your head without the write-up. Sometimes I let it go. But if you make a mistake, that means I couldn't find where the mistake was because you did everything in your head. I couldn't go into your head to find out what's going on. Then you're gonna get like the whole things without credits. So you see the point of me asking you to do a detailed write-up. That's because I want to be able to give you partial credits. So this is considered a mapping process. Quite the same when you have this moment in the equation, you have a reference point and you have a tag with the axis. So it's going to be, the way I'm going to write it is going to be a moment around z-axis, reference at point A. Either way, it means the same thing for me. So it doesn't matter which one you use, but you're going to have the governing equations for the moment as well. Now, in 3 dimensions, you will have 6 in total. In 2D, you will have just 3. At this point, z-axis coming out of the paper. So it means your moment would follow the 4 fingers on your right hand. So positive is always going to be like this. So your equation, some people would be doing this. This is definitely wrong. I'm not going to take it. Or some people do a skipping like this. This is also wrong. So do not do that. Just make sure that you complete the mapping process according to the axis of reference that it gives you. So in this case, I will have MA, and I will have, for example, like this one would be 0.4 meter, and then 200 Newton. Notice that I do write units on all this write-up. If you miss any single point of those write-up, that would be half a credits off, like half a points off. So do not miss those. I don't know about the other instructor, but I insist them on being very critical about checking all the detail, and hopefully they follow that same protocol. Any question before I test your skill on statics? Okay, Now I'm going to test your skill in statics. It's going to be very simple, straightforward. This is going to be a simply supported beam so again I will have 100 Newton, 50 Newtons, 100 Newton, and I will have this one right here going in, so this would be an X. This is 10 Newton meter. 150 millimeter, 200 millimeter, 200 millimeter. So this is exercise number 1. I'll mark the point A, B, C, and D. So my question is, find the reaction at support B and C. In your static class, this may take half an hour. In my class, this should take only 5 minutes because you need to have this fundamental knowledge before we proceed with anything else. So you cannot continue doing the problem solving in the same speed as what you did in the previous class. This has to be a lot faster with all those write-up as well. So even with all those write-up, I expect you to finish this in about 5 minutes. So, wake up the friends who already fell asleep and let us do this together. So this is exercise number 1. You will need to export the result of this exercise. I will ask you to submit this as part of the assignment today. So do this. If you don't have iPad, you can use a piece of paper, borrow it from your friends. Yes.
The axis, can I just draw it floating like this?
Yeah, it can be floating like that.
And the force 150 Newton is in the midpoint, right, of the object?
Yes, it's in the midpoint. 150 Newton is in the midpoint. The person hidden behind the column, can you see? Okay. Everyone has been through statics, right? We have one exchange. You had static class before? All right, good. thing that I do this as an exercise because I forgot to say something. So I'll let you finish this.
The beam has no width. No? The beam has no width.
It does not. It doesn't.
It has no width.
It's correct.ได้ไหมสามเหลี่ยมมันเป็นพีมีทั้ง y วงกลมเป็นโรลเลอร์มีแค่ y กูได้750มิลแบบ0.15เมตรเลยครับ
You should gauge your speeds. I think this is just about right in terms of the time that it should take you to do the write-up and everything. So, you need to do this as well. Next, you need to start grading yourself. So I'm going to start with the free body diagrams. Whenever you do a free body diagrams, you need to redraw. If you're using iPad, you can cheat a little bit, like this, for example. You need to redraw and make sure that you don't write forces, external forces or constraint forces over the existing picture. If you do, you get nothing. You get 0 for this part. So again, you need to have replace the physical constraints with the loads. So we have pin support and roller. You need to put axis. And then of course, in terms of the dimension, you need to put the dimension needed for the calculation. So for example, in this case, I will have 100 millimeter here. I will have another 100 millimeter. And then of course, this one is needed. That means this one, 200 millimeter. And the last one would be, this is 350 millimeter. So usually, you would want to put the dimension needed for the calculation. You don't need to put everything, just the one needed. So this part right here is considered 30% usually, regardless of whether or not you're doing statics or doing mechanics of material. In mechanics of material, you're going to have several free body diagrams, and many of them are easier to write. So, for example, if you have 3 different free body diagrams to write, each one of them would be like 10%. But this is an example. 30%, whenever you have any error on this free body diagrams, like missing the dimension, missing the axis, or missing the forces or the moment applied, you will have to take 0.5 out of 10, so take 5% off. So grade yourself for that. So that's the first. Always redraw. So second one, sum of the force in the x equal to 0, do the mapping process. I only have bx, this is 0. Usually if it's easy like this, I'll add like 10% to this. So you can do the grading yourself to see if you have this. And then of course you will need to do this. If you say sum of the force in the y, you will have 2 values. So usually when you start doing the write-up a little bit and feel that, hey, this single equation is not sufficient, you will delay that calculation and you will go for sum of the moment. And in this case, around B point, C axis equal to 0. And according to this, I will do the mapping process from left-hand side to the right-hand side. So this one will be 100 Newton. And then I'll have 0.1 meter. I noticed one of the ladies here, one of the guys over there didn't have units. Take points off whenever you don't have units on those. So again, this is going to be minus 50 newtons, again 0.1 meter. And then again, this is going to be my CY, 0.2 meter. And this is going to be minus, according to our sign, minus 10 Newton meter. And then the last one, minus 100 Newton. This is going to be 0.35 meter. And this is a complete mapping process. When you do a mapping process like this, it's very easy because if you write it from left to right, if there's any error, if there's anything that you need to check, you can always, do the check very easily. So doing the left to the right, like that. So in this case, I only care about the mapping process, the calculation part, you can punch everything in the calculator. I don't care. More detail than this. This is the only detail that I want. So in here, I would have 10 plus 35 plus 5 minus 10 divided by 0.2. 200, right? Check my work again. A lot of this I do it in my head as well. So 10, 35, 5 minus 10 divided by 0.2. Okay. So again, this is a little bit more difficult. Usually I would say this is about 20%. Usually, if it's a static part, or even 30%, but I'll finish this up later. In the last one, sum of the force in the y equal to 0. Mapping process, minus 100 plus By that I don't know, minus 50 Newton plus Cy, which is 200 minus 100 Newton equal to 0. So I'll get my By. And that is 50 Newton. And usually this will be roughly 20%. So 20, 20, 10, that's only 80. So usually in the end, I would increase this 60, still 90%. Usually I would try to make it even, so in the end would be like this. If this is 100%, it will be weighted like this. So grade yourself. If you miss any units, take 0.5 off from that. Again, you should have finished that in roughly 5 minutes. If you don't have it done in 5 minutes, that means you have to start thinking about practicing a little bit more, doing more training, because your problem will be a lot more difficult.
You need a conclusion, like a final conclusion.
If it's a big picture, for example, sometimes you need to have like ax equal to 0, bx equal to 0. Sorry about that. You need like a summary of everything like this.
Yeah.
Usually, if it's a big problem, a very big picture, I would be taking point like this, 10%, and I'll take like 10% from here. But at this point, the problem itself is very short, so I don't need like a summary of the result like this. But along the way, starting next week, I will definitely ask you to deliver the summary of the result of the analysis.
Do we have to put the units off after the 0?
Yes and no. I mean, if you put it there, that's a plus, but usually if anything's 0, I don't care about units anymore. But if you start having any number, then I check for units. But then yes, you should put like 0 Newton. You should. But I'm not that strict about 0. Other Ajahn are maybe strict. I like that as well. I like that. So to proper do this, 0 Newton. Yes. Okay, we're gonna take 5-minute break from here, and when we come back, I will do one more exercise to check your knowledge in statics. And then after that, I'll ask you to submit the in-class assignment from the 2 exercises. And then we'll start with the revisions of what we call, well, not a revision, it's going to be brand new, what we call engineering material for you guys. So 5-minute break, please. Get to the restroom is on the left and on the right. For those of you who've never been here.
You write your solution, you write Newton meter, you write Newton and then dash meter. Okay, just write Newton meter like this. Yeah. Okay. And this is going to be like some future problem, future question. In the shear force, does the shear force has to be connected to the